Hi again. We continue talking about offensive security, and today we have Piotr Głaska, who for the last 4 years has been doing extensive research into how DNS is being used as a tool and part of malware and APT attacks. So a very warm welcome to Piotr and his talk on how attackers abuse DNS in 2021 and 2022.
Hi, good afternoon. Thank you for the welcome. Let me first ask you, who has been on any of my presentations before? Okay, I see some faces. I even recognize some faces. So I'm old enough to be glad to recognize the faces, actually. So my name is Piotr Głaska. I work for Infoblox, which is a secure DNS vendor. And my area of specialization is how DNS is used by attackers and how DNS can be used by defenders as well. So today I'm going to share with you how I have seen attackers using DNS in last year or two. I'm actually not a researcher in a real term, so I'm not a malware researcher. I'm not doing reverse engineering and so on. But I did look at different threat reports, at different also domains and so on, and look how the attackers were using DNS in their attacks. So not a very broad view of things, but rather a very narrow one. Okay. So first, how in general DNS is used by the attackers, because normally, people think about DNS as a phone book of the internet, but actually it's very wrong, because DNS is not used just to resolve names to addresses. Even according to RFC, DNS is actually a distributed database. So you can send a query and you can get the result. It could be a name and you can get the address in the result, but could be anything else. From the attacker perspective, though, it could be even more, because it's just a method of bidirectional communication. So it doesn't have to be a query and the response, but actually the response can have a task sent to the client, and then the client in the query will actually send some information. So quite opposite of what we normally see. So looking at the cyber kill chain, there are several phases of the targeted attack. And in each of these phases, almost DNS is used at some point of time. For example, reconnaissance phase, attackers will use DNS to get some information about the victim's infrastructure, what IP addresses are used, especially from passive DNS. Sometimes you can even see private IP addressing, because basically, DNS is managed by humans. We do mistakes, so often you can find things which you shouldn't find inside. Names of the system can give you an idea what kind of security systems are used, what kind of applications are used, and so on. Then we have a weaponization phase where the attacker is preparing the weapons used in the attacks. So, he will prepare the malware, he will prepare some tools, register domain name from the perspective of DNS, set up DNS servers, set up C2 servers, and so on. Then we have a delivery phase. In this phase, attacker is delivering the malicious content to the victim. It could be an attachment to an email, doesn't have to be attachment, could be a link to malicious content. Usually, when this is the link, it usually is a fully qualified domain name instead of IP address. It sometimes can happen, it's an IP address, but more often than not, it's a name which needs to be resolved. And of course, first, at this stage, the defenders has some first options to act. Usually at the reconnaissance phase, not much can be done. But at the delivery phase, the defenders can use DNS to their advantage. Of course, it doesn't have to be an email, right? It could be a message on the LinkedIn from the headhunter, theoretically Facebook or whatever. Then we have an exploitation phase. And here, DNS might be exploited as well. DNS is usually some kind of a software. Could be a server-side software or the client-side software. And both can have, vulnerabilities. I will show one example of OT network actually, and the client vulnerability. These vulnerabilities can be used to execute remote code just based on the DNS reply, for example. That's a very common case. Then we have an installation phase where the malware is actually installed on the asset. Here, DNS is not used much. But the phase where actually DNS is used at most, in my opinion, is the C2, so command and control phase. Because first, the malware needs an IP address of the C2 server. Could be hard-coded in the malware, but again, more often we find, like, I don't know, in 80% of cases, more or less, that the name of the C2 is not necessarily hard-coded, but it's basically stored as a name, as a fully qualified domain name. So it needs to be resolved. This name could be hard-coded in the malware, but also could be downloaded from some external resources. This name could be also not downloaded, but actually can be generated on the fly. So instead of having an address of the C2 server inside of the malware, malware will generate randomly from random characters domain names, let's say 1,000 per day. Attacker knows how the code is generating those domain names, and he will register one domain name for a specific date. So the malware continues to generate those domain names, and finally it will generate the one which attacker has registered. Then it will be resolved to the IP address, and then malware knows where to connect. So it's called DGA, domain generation algorithm. Could be random characters, could be also random words, because then it's much more difficult to detect. Because if you generate something from random characters, someone can use, for example, entropy, n-gram distribution, a lot of things to detect that this is automatically generated. But when things are generated from the words, it's slightly more difficult. Finally, after the address of the C2 is known, the communication starts. So the infected machine will register itself in the C2, ask what should I do, get the task to be executed, and so on. This communication can happen also over DNS. So for example, DNS query from the infected host sent, well, indirectly, but finally to the C2 server, can contain, for example, registration message plus some reconnaissance info, like what user are we running on, what are the permissions, and so on. Then in the DNS reply, the C2 server can give back a task to be executed, do a screenshot, execute a command, and so on. And then in the queries from the client, the results of these commands will be sent to the C2 server. So that's C2 over DNS. And basically, most of offensive techniques which are using DNS, I find most of them in this C2 phase. Finally, we have actions on objectives. Attackers can, for example, steal some information, and they can send this information over DNS queries. So let's say hostname could have some encoded information inside, and then the C2 domain name is added. So when the query is sent to the DNS server will send it somewhere to the internet. Finally, it will reach the DNS server responsible for the C2 domain, and then the C2 server gets the query, extracts the data from the hostname or subdomain name part, and that's how the data is being sent. Also, DNS can be used to cause an impact on services, because basically DNS is one of the three most important protocols on the internet. If DNS doesn't work, basically nothing works. If external DNS doesn't work, external services doesn't work. If internal DNS doesn't work, then basically Active Directory doesn't work. So definitely could cause a huge impact. Let's look at some real-life examples, and we start actually from quite advanced one. That was described by Malwarebytes and Fortinet. So we have an APT34 group, which is an Iranian group. And in this attack, they were targeting Jordanian government. So basically, they sent an email to one of the government officials. This email was pretending to be sent from the IT guy. So they use a name of a guy which this government official known. I've actually, looking at these emails, we see first email saying, fill attached form to confirm received document as soon as possible. But actually, this email didn't contain the attachment. Then the other email was saying just attach file, right? So it's like, typical human error. I just forgot to attach a file. So probably that is building even more credibility in that. The attached file was an Excel file, which obviously was malicious. It was relying on user to enable a Visual Basic for Applications macro. What was important, though, because so far it's typical, what was interesting, though, is that each macro execution step was actually reported over DNS to the C2 server. So the macro was, after each significant step inside, it was sending a DNS query which could look like this one here. So we have 2 letters, which are just meaning that we are reporting these execution steps, then some step ID, and some random number, plus C2 domain name. So after every step, they knew that the macro was moving forward. So if any step would be not successful, they would basically know where it was stopped by the defenders, for example. Interesting also was that normally when you send DNS queries, you are using things like either DNS query win32 function, or you run nslookup.exe. That's most typical. In this case, though, they use the ping function to send a DNS query, because some EDR systems might count how many queries were sent from the application, because too many is basically suspicious. And in this case, they are sending ping. But to send a ping, first the name has to be resolved, so the DNS query is sent in the background. So basically, they achieve sending DNS query by running ping status function. In the past, I also have seen other malware doing that. That was PowerShell malware, and it was executing ping.exe, basically, to resolve a name into the IP address. The Excel was checking also if it is running maybe in the sandbox. So it was checking, for example, if the mouse is connected. If the mouse was found, then the Excel was dropping backdoor. Also, the backdoor was interestingly stored in the Excel because it was stored in the user form in the text box. Then there was a base64 encoded backdoor as a text. It was not run directly from the Excel. Instead, it was set as a scheduled task, run every 4 hours for 20 days initially. So it was finally executed by scheduler. The backdoor itself was a .NET binary. It could, just as a backdoor, could execute some commands, download some files. The commands could be either pre-coded, so it would be just enough to send a task number to be executed, or it could be a custom command, basically any command. Here we see how the DNS communication was looking like. So we have several queries and replies. You can see that this type of communication is quite typical to APT groups. Because if you would look at the very simple criminal groups and how they use DNS, then usually you see a very long DNS queries, because they try to put as many data as possible in the query. In this case, though, the query length is just normal, like even short ones, right? Also, the other interesting technique is that they change a domain name each time they send a query. All of these domains are probably served by the same DNS server, but basically, when someone is observing this traffic, it's not that suspicious that one host or one application is sending hundreds of queries to one domain. Here, it's basically they were changing domain names. IP addresses are different in each reply, and that's because these are not IP addresses, basically. It's just a task code or some kind of data stored as 4 bytes, as 32 bits, which are represented as an IPv4 address. But typically, when you look at the C2 over DNS traffic, you will see that the replies are usually built from different IP addresses, rarely repeated even. Second advanced characteristic of this of these APT34 actions are very long random delays. So between queries, they were waiting between 40 to 80 seconds. So, well, maybe not very long, because I have seen longer delays used by the APT groups, but it's definitely not a short one. They are not sending queries first. It's not a fixed delay, so it's not like every second, and it's not very short, like a second, 2, or something like that. Failed communication would cause even delay of 6 to 8 hours. They basically went quiet. The queries were built from the content, counter, and one of the domains. They use 3 different domains. They were not fresh domains, because sometimes we can see, especially simple criminals, that they like to use, or they have to use, domains which they just registered yesterday, or 2 days ago, or 10 minutes ago. In case of APT groups, of course, it's not the case. They have the money, resources, and so on, so they will register domain name a month, a half a year before the attack. They might even, use it for some good purposes, so it will have a good reputation. And in this case, it was around 2 to 3 months before the attack. The counter here, it was encoded with base 36 algorithm, which contains basically letters, lowercase letters, and digits, typically. But in this case, they use a custom alphabet, as you see. So they basically use some random characters for the base 36 alphabet. And all the comments, they were, so the content basically was also encoded with some simple substitution, but the alphabet used for the substitution was generated with this counter. So basically, it was ever-changing. Finally, results of the comments, also interesting. Results of the comments were compressed to, not to take so much data in DNS traffic. They were base 32 encoded and sent as DNS queries. So basically, hostname part in a DNS query would contain data. This data was base 32 encoded and presented as a hostname. C2 domain name was added, and then it was sent. Also interesting thing is that if you look at the list of tasks which were pre-coded in the malware, task 13 and 14 and many others as well, they contained comments with some hard-coded internal domain names and IP addresses. So definitely it was not a first touch of this group with this victim. They did good reconnaissance. They knew what are the, for example, names of internal hosts, like ICE posture, probably Cisco ICE there, internal IP addresses, and so on. So that was hard-coded in the malware, and that's proof that the reconnaissance phase was well done by this group. Right now, actually, they would not need to, of course, rely on the user allowing macros, because as probably everybody heard a week or 2 weeks ago, there was Folina vulnerability discovered, which can be used to execute something from the, for example, Word document without any user interaction. Even the user doesn't have to open the document. It's just enough to have a preview in the Explorer, for example, to run a code. Okay, another example. This one is from Ukraine. It was reported by Ukrainian CERT, Invisible Group. It's active in Ukraine for a few years at least. This case is fresh from March 2022. Invisible Group here sends an email with an attachment, which was actually a shortcut, as you see, to MSHDIEXE and remote content. Finally, they are using different tools, and one of the tools I want to show, it's actually one I already shown in the past, so that's why I was asking about who was on some previous presentations. So basically, Invisible Group likes to use DNS for downloading additional malicious tools. So after they are inside, they want to download some additional functionalities, additional modules. Then basically, they do it this way that the infected client will send a DNS query to local DNS resolver of the victim. This resolver will try to resolve this name on the internet. And finally, it will send a DNS query to attacker-controlled name server. This name server, in the reply, will put encoded new malicious module, and then send this reply back to the local DNS resolver of the victim. The victim's resolver will just pass this reply to the client. And then the client gets the data from the C2 server, right? And then you get several replies, you build the whole tool. So this is how they use DNS. This is actually a very important part of C2 over DNS technique. It does not have to have direct connectivity with the C2 server. Here, this client could be an isolated network segment, might not have internet connectivity at all. It's enough that it can just send a DNS query to local DNS resolver, then this resolver will send this query to the internet, get the reply, and pass this reply back to the client. So basically, DNS is working by default as a multi-hop proxy. There could be several such DNS resolvers, and they would pass the message further. So it's very useful attribute of the DNS traffic. The attacker does not need to send a DNS traffic directly to the C2 server. It might just pass it to the first DNS resolver, and then the resolver pass it further. And this is often forgotten by the defenders. We need to check if in the isolated network segment there is a possibility to resolve an internet domain name. So you do just nslookup google.com. If you get the answer, then you have the problem. You need to make sure it's completely isolated. Also in OT networks, for example, this is a common mistake. OT network usually is able to use, for example, local Microsoft DNS to resolve internet domain names, and then they get the communication. Okay. Flubot. So this is one of the most advanced banking Trojans, actually. Luckily, current infrastructure was shut down a week ago, I believe, with combined cooperation of 11 countries. But let's look at it because it's quite interesting. So basically, it's targeting Android platforms and basically end users trying to get access to the bank accounts. It usually pretends to be either a DHL delivery app or the voicemail app. So people usually get a text message saying that you have a voice message and click here to listen to this message. Then they are asked to install the application for the voicemail, and this is how it starts. Then it will replace a default text application, and it is controlling text messages so it can spread by sending itself to all people from the phone book. It will also send a list of installed applications to the C2 server, and then the C2 can send a specific injects for a specific application. And it is using a lot of different advanced techniques, especially in terms of DNS. For example, it is using the DGA algorithm, which I mentioned before. So basically, the malware does not store a name of the C2, but instead, it has a small algorithm which is capable of generating 5,000 domain names. In this edition, they were ending with .ru, .su, or .cn, so a little bit suspicious for a lot of people. It is also using C2 over DNS, and not only over DNS, but actually C2 over DNS over HTTPS. So instead of just sending those hidden communication over DNS queries, they were also using DNS over HTTPS. Two basically known open resolvers on the internet. So as you see here, the queries were sent over HTTPS to Cloudflare DNS, one of the two most popular DOH resolvers. So one is Google, second is Cloudflare, because one is used by the Chrome, one is used by the Firefox. They are most commonly used DOH resolvers, also by malware, actually mostly these two only. So here we see a DOH query Here we have a name which was actually queried. So we have a very long name. So remember what I told before, that usually simple criminals will build very long queries. And this is the case here. Then we have a DGA-generated domain name and the type of the record and so on. Each request to the C server would use a different key for the encryption. So it's not so typical for simple criminals to see, DGA, C2 over DNS, C2 over DNS over HTTPS, changing keys. So quite, bunch of advanced techniques used by actually quite simple criminal group. 2 months ago, there was a report about first malware found targeting AWS Lambda serverless functions. That was malware written in Go. And basically, it was a simple thing. It was just trying to mine cryptocurrency. It was not really, abusing any functionalities of Lambda. It was relying that someone has some credentials allowing him to run this code as someone else Lambda resource. Here they use DNS over HTTPS to resolve mining pool domain names. Basically, probably they use DOH because it allows to send DNS queries even if they are not allowed. For example, port 53 could be blocked, but maybe HTTPS would be allowed. And also, in many cases, the provider of the infrastructure might not have the visibility inside of the DNS queries. That's the case in Flubat as well. So basically, service providers are not seeing the queries sent by the malware because it is using DOH. So also important thing for the service providers. I mean, if you provide a secure DNS functionality, then there should be, with this, it should be included blocking of public DOH resolvers. Yeah? So if the customer, end user, wants to have security based on DNS, there should be a filtering of any packet to quad 1 IP address, quad 8, quad 9, and so on. OK, so here, very simple usage, just interesting case, because first malware running on Lambda. Crypto mining could be fruitful for the attackers. That's another example of the malware. Krakonosh, it was found by Avast. 200,000 infections, and they were successful in mining at least $2 million. So it's a reasonable amount of money. And they use DNS to get address of the server with a new malware module, basically. So malware was checking if there is any new version of it. And the checking was done by sending a DNS query to this hostname, txt query. And then there will be an IP address of the update server, the port of the update server, and the latest version of the malware on this server. So basically, it was like an update function. And again, prove that DNS is basically just a distributed database. Yeah? You just ask about something, you get something. Doesn't have to be an address or anything like that. DNS was also used in interesting ways in different malicious packages in public repositories. So here we have an example of scanning PyPy repository, Python packages repository. And here the JFrog company, which was doing this scan, they found several different malicious packages available publicly. And they were usually quite popular, to be honest. For example, you have like 12,000 downloads, 10,000 downloads. So not good. 2 of these packages were using DNS to send some information from the machine of the victim to the C2 server. For example, here we have information such as hostname, current working directory, IP address, the public one and the private one. They were sent as part of DNS query from the system on which this package would be installed and executed. This is quite typical with the dependency confusion attack. So what is dependency confusion attack? Last year, one threat researcher, Alec Beerson, has published a research about basically ability to run your code on someone's machine based on packages downloaded by the developer. For example, if the name of the package the developer is using is the same in the local company repository and public repository, then different developer tools might reach to either first local repository and then public, or quite opposite, might first look at the public repository and then the local repository. Could be also dependent on the version of software, right? So it will look in the local, in the public repository, and just get the newer one. That's why here we see a version 999 on the public repository. Because if someone in the local software repository will have a 1.0 version of PP test package, then basically some tools might actually reach to the external one because there is a newer version and then get the malicious one. So Alex was quite successful in his proof of concept because he was able, with this technique, he was able to basically run his code in Apple, Microsoft, Netflix, PayPal, basically all of the major companies. And he was able to run this code very deep inside of their networks, because usually it was, some developer quite deep inside of the infrastructure. All of them were vulnerable. And he chose an interesting way how to send some data from these deep segments of the network to his server. He chose to use DNS because he was thinking like, I don't need direct communication then. I will just send DNS query to local DNS server and it will do the job for me. So even if there were several layers of firewalls, he still was able to exit the network and send some information. Okay. Another example, it's a Linux backdoor using C2 over DNS, and it is also using quite recent log4j vulnerability to execute the code. It has functionalities such as backdoor, so it can execute the code, can download something, upload something, could install SOX5 proxy, so infected host can basically pass some data. Data exfiltration was also possible, rootkit installation, and so on. DNS was used here in a few ways. So by default, the malware would take some data to be sent from the infected host, so either sensitive information or just a result of command execution. The data would be then compressed, encrypted, then base64 encoded, and then just used in the hostname part. This encrypted and encoded data would be put in the hostname part, C2 domain would be added, and the query would be sent. Default method was to use Google's DNS, so public open resolvers, Quad 8, 8844. Interesting though is that they were using TCP DNS queries. So most typically DNS queries are sent over UDP, but TCP is also a viable option, especially for C2 communication, because it provides you with retransmission, reordering, everything what TCP brings with it. So you don't have to worry about that. And also with TCP, you can actually send much bigger DNS queries. Even 64 kilobytes are possible. If that would not work, though, there was a backup path to send the query directly to the C2 server. It was also TCP DNS query, but interestingly, it was sent over port 443. So HTTPS port, but it was not HTTPS traffic. It was not DNS over HTTPS. It was just pure DNS, just the port was 443. If that would not work, then they would switch to the local DNS and send normal UDP query. So here we have a traffic sample of the traffic. 2 queries for google.com. It was basically keep alive. So the malware was asking the C2 server about google.com. That was, let's say, kind of keep alive. Then we have some data, base64 encoded, as you see, and some domain which they used. Base64, it's not ideal from the perspective of the attacker, because usually DNS is used to resolve names to IP addresses. RFC is highly recommending that DNS queries should be built from letters, and it should be case insensitive, and digits. And should not contain, uppercase characters, should not contain any signs, characters such as plus or slash, anything like that. It's allowed, though. I mean, RFC is not saying you cannot use that. You can, and 99.9% of DNS systems on the internet will accept that. But from the defender's perspective, if you see something like, case-sensitive names in the DNS query, you see a slash, plus, any special sign, it's obviously an anomaly and needs more caution, to have a more look into that. Okay, Lyceum APT group. It has a lot of similarities to APT34, which we started with. Also, Iranian APT group. They are attacking telecommunication operators, critical infrastructure in the oil and gas sector. In this attack, they targeted telcos and airlines in Tunisia. So usually, this is sign, the sectors attacked here, this is a sign of a government-backed group, because they might attack government agencies, but usually when they need to, for example, get some information about some people, they will attack airline because they want to know where the people are flying, when and where this person is flying. They will attack telco because they want to have a billing from his mobile phone, right? They might attack a financial institution, like a bank, to get an idea about wire transfers this person is getting or sending, and so on. So that's quite typical. Here they use C++ backdoors and a PowerShell script. They were using C2 over DNS, or because there were several variants. Some variants were using C2 over DNS, some variants were using C2 over HTTP, some variants were capable of doing both. If one would fail, then they would just switch to the other channel. Interesting, though, is that the C2 communication was basically decoupled from the protocol, DNS or HTTP. They basically used DNS or HTTP to send files which contained the C2 communication inside. Just as a backdoor, it could execute some commands, download, upload files, drop additional tools such as Mimikatz-based to steal some passwords and so on. And here we see how the DNS was used. They were using 2 query types, A and TXT. So basically the most popular ones. A is the most popular one. TXT is also a very popular one. And they store the data such as, for example, task to be executed, action code, victim ID, that was encoded with base32. Basically, from what I have observed, base32 is the most popular method of encoding data by APT groups in DNS queries. The reason is that base32 is using just lowercase letters and digits, so it perfectly fits DNS queries. Base32 normally contains standard letters A, B, C, D, and so on, and digits from 2 to 7, 2, 3, 4, 5, 6, 7. But here they were using custom alphabets, like the one here. So basically it's some random characters, and each variant was using different alphabet, so different character set. Also quite typical behavior of APT groups. They were using, depending on the variant of the malware, they were either sending these queries with NSLOOKUP or with DNS query API calls. So slightly different than APT34, which was using ping to make it in a little bit more clever way. They were seen also active recently, and they were using topics from Ukraine war. For example, middle of March this year, they sent an email to Israeli energy company with a subject, Russian war crimes and so on. And this email contained a link to malicious document, which was dropping a backdoor in the startup folder. So next time the victim was restarting the computer, then the backdoor was initialized. So they were not executing it immediately, but rather use the startup folder for that. Okay, last example. Slightly different story. It's about exploitation faced in the cyber kill chain. So this is InfraHalt. It's a set of vulnerabilities found in some TCP/IP stack of basically OT devices or ICS devices. It was found in a stack named niche stack. It is used, for example, in Siemens S7 programmable logic controllers. There is a bundle of vulnerabilities, 14. 5 of them are related to DNS. And to show you what is all about here, it's basically a proof of concept of this vulnerability. The idea was to initiate FTP connection from infected device. To do that, the DNS query was sent by the tested device, so this device with the niche stack, to DNS server with address 8008. Then, normally, you expect to get a reply from the IP of the server which you sent the query, right? So normally you expect to have an answer from 8008. And the client should only take the reply if it comes from 8008, it comes on the same UDP port which we send the query from, and also it should contain the same DNS transaction ID. So there are 3 things, basically, which makes this a connection. In this case, as you see, the reply comes from completely different IP address, man-in-the-middle attack. And it is accepted by the device. So it is not even checking if the IP is the same like we send the packet to. Then another vulnerability was around DNS transactions ID. They were not random. And UDP source ports were also very easy to guess. So basically, a small disaster here. That's why we see an FTP connections being started because the code is executed. The packet also contained compression pointer exploitation, which makes it possible to execute the code which was sent in the DNS reply. Plenty of such exploits recently. 2 years ago, it was found in Microsoft DNS. Also, you could just send a DNS reply and execute code with local system privileges on AD controller running Microsoft DNS. The same in OT devices. So basically, it's quite popular now. And the problem here is that you don't need a direct access to this device, right? It's enough that this device will send a query to the internet. You make sure you send a reply, like in this case, just as a man-in-the-middle attack. You send a DNS reply, and even though this host is far away in OT network, it is getting the reply, the code is executed, and then you start C2 over DNS communication. And again, you don't need direct internet connectivity because you use local DNS as a proxy for your communication. So that's a problem with DNS in isolated network segments. We always have to remember that you need to check if you are able to resolve a name from the isolated network segment or not. If yes, then there is communication possible in both directions, actually. Okay, that's all from my side. So if there are any questions, queries, there are no bad queries.